Welcome! In this session, we'll explore an interesting problem, kth smallest element in a sorted matrix. This problem challenges us to efficiently navigate through a matrix that's sorted both row-wise and column-wise to find the kth smallest element. By the end of this walkthrough, you'll gain insights into multiple approaches and their trade-offs. Let's get started. In this problem, we are working with an nxn matrix, meaning the matrix has the same number of rows and columns. What's unique about this matrix is that both the rows and columns are sorted in ascending order. Your goal is to find the kth smallest element within this matrix, where k is a 1-based index. This means k is guaranteed to be a valid position, so it's always between 1 and the total number of elements in the matrix, which is n squared. To summarize, the input consists of the matrix itself, which is a 2D list of integers, and the integer k, which specifies the position of the smallest element you're tasked to find. The output will be a single integer, representing the kth smallest element. Let's take a look at some examples to understand this better. In the first example, the given matrix is a 3x3 grid, where each row and column is sorted in ascending order. The value of k is 8, so we need to find the 8th smallest element. If we flatten the matrix and sort all of its elements, we get a sorted list: 1, 5, 9, 10, 11, 12, 13, 13, 15. From this sorted list, the 8th smallest element is 13. Therefore, the output for this example is 13. This demonstrates how the kth smallest element is determined by considering the sorted order of all elements in the matrix. In the second example, the matrix is a 2x2 grid, and the values are all negative numbers. Here, k is 2, meaning we need to find the second smallest element. Flattening and sorting the matrix gives us the list, -5, -4, -3, -1. From this list, the second smallest element is -4. So, the output for this example is -4. This highlights that the approach works regardless of whether the matrix contains positive or negative numbers, as long as the rows and columns are sorted. In the third example, the matrix is again a 2x2 grid, but this time the values are consecutive positive integers. The value of k is 4, so we need the fourth smallest element in the matrix. Sorting all the elements gives us the list 1, 2, 3, 4. From this list, the fourth smallest element is 4. Therefore, the output is 4. This example shows that when k equals the total number of elements in the matrix, the answer will simply be the largest value in the matrix. Now, let's discuss some edge cases to consider. For a very small matrix, such as 1, with k equal to 1, the answer is straightforward because there's only one element. For larger k values, like in a 2x2 matrix where k equals 4, the kth smallest element corresponds to the largest element in the matrix. If the matrix contains negative numbers, such as -10, -5, -4, -2, with k equal to 3, the sorting process still works as expected, and the result is -4. Finally, if the matrix contains duplicate values, such as 1, 1, 1, 1, with k equal to 3, the duplicates are included in the sorting, and the kth smallest element can be one of those repeated values. These edge cases demonstrate the importance of handling different types of input while ensuring the solution remains efficient and correct. To begin solving this problem, we first consider the brute force approach. The intuition here is to rely on the fact that the matrix is already sorted row-wise and column-wise. By flattening the matrix into a one-dimensional list, we can sort all the elements and directly access the kth smallest element by its index, which is k1 when using zero-based indexing. The steps are straightforward: flatten the matrix, sort the resulting list, and return the element at the desired index. However, this approach has significant drawbacks in terms of efficiency. Flattening the matrix takes n squared time, and sorting the resulting list requires n squared log n squared time, resulting in an overall complexity of n squared log n squared. Additionally, it requires n squared space for the flattened list. While this method is simple and easy to code, it is not practical for large matrices due to its high time and space demands. The brute force approach, while straightforward, is inefficient for larger matrices. This brings us to a more refined strategy using a heap-based approach. The key idea here is to leverage a min-heap for efficiently managing the smallest elements in the matrix. We start by adding the smallest element, which is the top left element of the matrix, into the heap along with its coordinates. Then, we perform k iterations where, in each iteration, we extract the smallest element from the heap and add its valid neighbors to the heap. By the end of these k iterations, the kth smallest element will have been extracted. This approach is much more efficient than brute force, with a time complexity of k log n, since each heap operation takes logarithmic time and the heap size is bounded by the matrix dimension. The space complexity is n, as the heap stores at most one row or column at a time. This method is better suited for larger inputs and makes good use of the matrix's sorted structure. The heap-based approach offers significant improvements in efficiency, especially for larger matrices, and it effectively utilizes the sorted structure of the input. However, it is slightly more complex to implement due to the need for careful management of heap operations and valid neighbors. Another highly efficient strategy we can consider is the binary search approach, which operates directly on the value range of the matrix rather than the indices. The main insight here is that we can count the number of elements in the matrix that are less than or equal to a given value, mid, by leveraging the sorted property row by row. Using this count, we can adjust our search range dynamically. This method narrows down the value range until the kth smallest element is identified. By avoiding explicit storage of intermediate results and focusing on the value-based binary search, this approach is both space-efficient and computationally efficient. In the binary search approach, the first step is to define the search range as the minimum and maximum values in the matrix, which are the top left and bottom right elements, respectively. We then repeatedly calculate the midpoint of the current range and count how many elements in the matrix are less than or equal to this midpoint. This counting can be done row by row, taking advantage of the sorted order within each row. If the count is less than k, it implies that the kth smallest element must be in the upper half of the range, so we adjust the range to exclude the lower half. Otherwise, we adjust the range to exclude the upper half. This process continues until the range converges, and the kth smallest element is found at the lower bound of the range. The time complexity of this method is log max min asterisk n, where max min is the value range, and each counting operation takes n time. Additionally, the space complexity is 1, as no extra data structures are required. This makes the binary search approach highly efficient for large matrices. After evaluating all the approaches, we chose the binary search strategy as the optimal solution for this problem. It offers the best balance between time and space efficiency, particularly for larger matrices, due to its logarithmic factor. While the heap-based approach is also efficient and slightly easier to implement, it does not match the scalability of binary search for very large inputs. On the other hand, the brute force approach is too slow and impractical for competitive programming or real-world scenarios where performance is critical. However, we do acknowledge the trade-offs. Binary search requires a deeper understanding of value-based searching and efficient row-wise counting, which might make it less intuitive for some developers. The heap-based approach, with its simpler logic, might be preferred for smaller matrices or cases where implementation clarity is prioritized. Nonetheless, by taking full advantage of the matrix's sorted structure and minimizing unnecessary computations, the binary search approach emerges as the most efficient and scalable choice for this problem. To solve the problem of finding the kth smallest element in a sorted matrix, we can start by considering a brute force approach. In this method, we take advantage of the fact that the matrix is sorted row-wise and column-wise. The first step involves reading the input, which is an nxn matrix along with the value of k. For example, given the matrix 1, 5, 9, 10, 11, 13, 12, 13, 15, and k equal to 8, we observe that the rows and columns are sorted in ascending order. Next, we flatten the matrix into a single one-dimensional list. This is done by traversing each row and column, effectively combining all the elements into a single array. For the given matrix, the flattened list becomes 1, 5, 9, 10, 11, 13, 12, 13, 15. This transformation sets the stage for treating the problem as finding the kth smallest element in a straightforward array. Flattening the matrix allows us to focus on a simpler task, finding the kth smallest element in a one-dimensional array. The next step is to sort this flattened list using an efficient sorting algorithm. Python's default sorting algorithm, timsort, is both stable and efficient, making it well suited for this task. Once the list is sorted, it becomes 1, 5, 9, 10, 11, 12, 13, 13, 15. With the elements now in ascending order, retrieving the kth smallest element is straightforward. Since k is 1-based, the kth smallest element corresponds to the element at index k1 in the sorted list. For our example, where k equals 8, the 8th smallest element is at index 7, which is 13. Finally, we return this value as the result. Edge cases are also important to consider. For instance, if k is less than 1 or greater than the total number of elements, the input is invalid and should be handled appropriately. Additionally, the algorithm naturally accommodates duplicate values since sorting inherently organizes them in the correct order. This brute force approach is simple and intuitive, but it's important to recognize the key insights that make it work. First, the properties of the matrix play a significant role. While the matrix is sorted row-wise and column-wise, its global order is not immediately apparent. Flattening and then sorting reconstructs this global order, making it possible to identify the kth smallest element. Sorting guarantees correctness because the elements are fully arranged in ascending order, ensuring that the kth element is accurately retrieved. However, this simplicity comes at a cost. The approach is computationally expensive, with a time complexity of n squared asterisk log n squared due to the sorting step. This can make it impractical for very large matrices. From a data structure perspective, the flattened matrix is stored in a one-dimensional array, which serves as the input for the sorting algorithm. TimSort is utilized here, chosen for its efficiency and ability to handle real-world data effectively. Analyzing the complexity of this brute force approach reveals its limitations. The time complexity is dominated by the sorting step, which takes n squared to flatten the matrix and n squared asterisk log n squared to sort it, resulting in a total complexity of n squared asterisk log n squared. The space complexity is also significant, requiring n squared additional space to store the flattened list. These factors make the approach less suitable for very large matrices. To address these limitations, we can consider optimizations or alternative methods. For example, a min-heap can be used to reduce the time complexity to k asterisk log en, or a binary search on the range of values within the matrix can achieve n asterisk log max-min. These methods are more efficient but come with increased implementation complexity. By fully understanding the brute force approach, we gain valuable insights that help in selecting the most appropriate solution based on the problem constraints and input size. This is a Python implementation for LeetCode problem number 378, kth smallest element in a sorted matrix using a min-heap approach. Here's a detailed explanation. 1. Imports and class definition. We import the heap module for heap operations and define the solution class containing the kth smallest method. 2. Input parameters. The method takes matrix, the 2D list where rows and columns are sorted in ascending order, and k, the position of the smallest element we need to find. 3. Initialize the min-heap. We create an empty min-heap, min_heap, and populate it with the first element of each row. Since the matrix is sorted row-wise, we only need the first column initially. We push elements as tuples, value, row, call, to track their position in the matrix. 4. Heap operations to find kth smallest. We repeatedly extract the smallest element from the heap, using heap.heappop, until we have extracted k elements. Each time we pop an element, we check if there is a next element in the same row. If so, we push it into the heap to maintain our sorted order. 5. Return the kth smallest element. After k iterations, the last popped element is the kth smallest, which we return. #### key details. The heap ensures efficient extraction of the smallest element in log n time. We perform this operation k times, leading to a time complexity of approximately k log n. The space complexity is min k n because the heap holds at most one element per row, up to k rows. This implementation efficiently handles the constraints of the problem while leveraging the sorted structure of the matrix for optimal performance. Here, we are implementing the solution to find the kth smallest element in a sorted matrix using Java. First, we import the priority queue class, which will be used to create a min-heap. In the method kth smallest, we begin by determining the size of the matrix n, which represents the number of rows in the square matrix. Next, we initialize a min-heap, which will store elements as arrays containing the value, row index, and column index. This allows us to easily track the smallest elements while maintaining their positions in the matrix. We then populate the heap with the first element of each row. However, we only consider the first column and limit the number of rows added to the heap to the smaller of k or n, as we only need enough rows to find the kth smallest element. Each entry in the heap is represented as an array, value, row, col, where value is the matrix element, and row and col are its indices. This setup ensures that the smallest elements will always be extracted first during the process. After initializing the heap, we repeatedly extract the smallest element from the heap until we have performed this operation k times. Each time we pull an element, we store its value in val and retrieve its row and column indices. If the current element has a next element in its row, we add that next element to the heap, ensuring the heap remains populated with the smallest available elements. This process continues until we extract the kth smallest element from the heap. At this point, the variable val holds the value of the kth smallest element, and we return it as the result. This approach ensures an efficient solution by leveraging the properties of the min heap and the sorted nature of the matrix rows. Here, we have a small 3 by 3 matrix and need to find the fourth smallest element. First, we initialize the size of the matrix, n, as 3 since there are 3 rows and columns. Then, we create an empty min heap to help us efficiently track the smallest elements. Next, we add the first element of each row into the min heap. These elements are 1 from the first row, 10 from the second row, and 12 from the third row. Each entry in the heap stores the value along with its row and column indices. After adding these elements, our initial min heap contains the tuples 1, 0, 0, 10, 1, 0, and 12, 2, 0, which means the heap now organizes these values for quick access to the smallest element. Now, we extract the smallest element from the min heap a total of 4 times, because k equals 4. In the first extraction, we remove the smallest value, which is 1, from row 0, column 0. Since there's another element in row 0, we push the next column value, 5, into the heap. The heap reorganizes to contain 5, 12, and 10. On the second extraction, the smallest value is now 5, from row 0, column 1. Again, we add the next column value from row 0, which is 9, maintaining the heap structure. For the third extraction, the smallest value is 9, from row 0, column 2. Row 0 is now exhausted, so we don't add anything new. The heap now contains 10 and 12. Finally, the fourth extraction gives us 10, from row 1, column 0. From row 1, we push the next value, 11, into the heap. At this stage, the fourth smallest element is determined to be 10, and we return this as the result. In this example, we're working with a larger matrix, and k is set to 6. Again, we initialize n as 3 since the matrix is 3 times 3. We create an empty min heap and add the first element of each row to it. These are 1 from row 0, 2 from row 1, and 4 from row 2. Each of these elements is added as a tuple with its value and corresponding row and column indices. After this step, the min heap consists of 1, 0, 0, 2, 1, 0, and 4, 2, 0, which are the smallest elements from each row. We now extract the smallest element from the heap 6 times to find the sixth smallest value. For the first extraction, we remove 1 from row 0, column 0, and push the next value from row 0, column 1, which is 3. The heap reorganizes to contain 2, 4, and 3. Next, we extract 2 from row 1, column 0, and push the next value from row 1, column 1, which is 6. The heap now holds 3, 4, and 6. In the third extraction, we remove 3 from row 0, column 1, and push the next value from row 0, column 2, which is 7. The heap updates to 4, 6, and 7. For the fourth extraction, we remove 4 from row 2, column 0, and push the next value from row 2, column 1, which is 5. The heap now contains 5, 7, and 6. The fifth extraction yields 5 from row 2, column 1, and we push the next value from row 2, column 2, which is 9. The heap becomes 6, 7, and 9. Finally, the sixth extraction removes 6 from row 1, column 1, and we push the next value from row 1, column 2, which is 8. At this point, we've extracted 6 elements, and the sixth smallest element is 6. In this edge case, k is set to 1, meaning we only need to find the smallest element in the matrix. The matrix remains a 3 by 3 grid, so n is initialized as 3. We start by adding the first element of each row to the min heap. These are 3 from row 0, 8 from row 1, and 11 from row 2. These elements are stored as tuples with their respective row and column indices. After this step, the min heap contains the tuples 3, 0, 0, 8, 1, 0, and 11, 2, 0, representing the first elements from each row. To find the smallest element, we perform just one heap extraction since k equals 1. The first and only extraction removes the smallest value, 3, from row 0, column 0. We then push the next value from row 0, column 1, which is 6, into the heap. The heap now contains 6, 11, and 8. Since we've completed one extraction, the first smallest element is determined to be 3, and we return this as the result. Here, we break down the time complexity of the heap-based solution. First, during the initialization step, we build a min heap by inserting the first column elements from the first min, k, n, rows. Since each insertion into the heap takes logarithmic time proportional to the heap size, the total time for this step is O, min, k, n, asterisk log, min, k, n. Next, to extract the kth smallest element, we perform k heap pop operations. Each pop operation takes logarithmic time, and if there's a next element in the same row, we need to push it into the heap, which also takes logarithmic time. Combining these, the extraction step has a total time complexity of O, k asterisk log, min, k, n. Adding both steps together, the overall time complexity of this solution becomes O, k asterisk log, min, k, n. In the worst-case scenario, where k is very large, approaching the total number of elements in the matrix, the complexity becomes O, n squared asterisk log, n, as the heap size can grow significantly. On the other hand, in the best-case scenario where k is small, the complexity simplifies to O, k asterisk log, n, because the heap operations only involve a small portion of the matrix. Now, for space complexity, the primary factor is the min heap, which holds at most min, k, n, elements at any given time. Each element in the heap is a tuple containing the value, row, and column, so the total heap space is O, min, k, n. The input matrix itself doesn't require extra space, as we directly access its elements in place, contributing O1 to space usage. Thus, the overall space complexity of the solution is O, min, k, n. To understand the efficiency of this approach, let's compare it to the brute force method. A naive approach would involve flattening the entire matrix into a single list, sorting it, and then accessing the kth smallest element. Flattening takes O, n squared, while sorting the flattened array adds O, n squared asterisk log, n squared. This makes the total time complexity O, n squared asterisk log, n squared. Moreover, the flattened array requires O, n squared, space. In contrast, the heap-based solution leverages the sorted structure of the matrix. Its time complexity, O, k asterisk log, min, k, n, is significantly better for large matrices, and its space complexity, O, min, k, n, is far more memory efficient. By optimizing both time and space, this approach is better suited for real-world applications. Combining these insights, the overall time complexity of the heap-based solution is O, k asterisk log, min, k, n. This approach avoids unnecessary computations, like sorting the entire matrix, while efficiently narrowing down to the kth smallest element. By leveraging the properties of the sorted matrix and using a heap to focus only on relevant elements, we achieve significant gains in both time and space efficiency compared to naive methods. This makes the heap-based approach a practical and optimized solution for finding the kth smallest element in a sorted matrix. When solving this problem, there are several common mistakes to watch out for. First, it's important to remember the matrix's sorted properties. If you ignore these and treat the problem like a generic find the kth smallest task, you might end up using inefficient approaches like flattening the matrix and sorting it, which can lead to a time complexity of O, n squared log n. Another frequent issue occurs during the flattening process itself. Some developers forget to maintain the original order of the elements, which can result in incorrect results unless the list is sorted again. For those using binary search, inefficiencies often arise in the implementation of the counting function, where a naive O(n) approach is used to count elements row by row instead of leveraging binary search within each row. Additionally, edge cases are easy to overlook. Situations like matrices with only one row or one column, matrices with duplicate elements, or when k is the smallest or largest possible value. Finally, some solutions fail to check if k is within valid bounds. For instance, k must be between 1 and n*m. Failing to validate this can lead to runtime errors or unexpected behavior, so always consider these scenarios in your implementation. Now, let's focus on what interviewers often look for when this problem comes up. Efficiency is a key factor. They expect you to optimize both time and space complexity, so approaches like binary search on the value range or using a min-heap are highly valued. It's important to demonstrate an understanding of the trade-offs between these methods. For example, a heap-based approach tends to be straightforward to implement but consumes more memory, while binary search on values is more space-efficient but requires careful attention to the counting logic. One of the best ways to stand out is by highlighting the matrix's sorted properties and explaining how these enable efficient strategies like binary search or row-wise counting. Additionally, make sure you're comfortable with the counting logic itself. Writing and debugging the count of elements less than or equal to mid function is a critical part of the binary search solution. To build your skills further, consider exploring related problems. For instance, LeetCode 378, which is the core problem we're discussing, is directly connected to problems like LeetCode 295, where you work with heaps, or LeetCode 240, which also involves searching a sorted matrix. Another interesting problem is LeetCode 373, which focuses on k selection using heaps and sorted arrays. Finally, let's discuss some alternative approaches and their trade-offs. The heap-based approach is a popular choice, with a time complexity of O, k log n, and a space complexity of O, n, for the heap. It's simple to implement and works well for smaller matrices, especially when k is relatively small compared to the total number of elements. However, it does require extra space, which might not be ideal for larger inputs. Another option is binary search on the value range, which is more efficient in terms of space, with a complexity of O, 1. Its time complexity is O, n log, max, min, where the logarithmic factor comes from searching the range of values and the linear factor from counting elements in the matrix. While it's memory efficient, this approach requires a solid understanding of the counting logic, which can make the implementation slightly trickier. Lastly, there's the flatten and sort method, which is the simplest to implement but also the least efficient. With a time complexity of O, n squared log n, and a space complexity of O, n squared, it's more suited for brute force or baseline solutions. While it's not practical for larger matrices, it can be a helpful starting point for understanding the problem structure before moving to more optimized techniques. Great job completing this session. Today, we explored the problem of finding the kth smallest element in a sorted matrix. We reviewed multiple approaches, from brute force to more optimized methods like binary search and heaps. Remember, understanding the problem's constraints is crucial to selecting the right algorithm. Thanks for watching, and be sure to like and subscribe for more problem-solving tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!